All right, we're going to start chapter 26 today, and we're going back to talk about categorical variables. So the last time I talked about categorical variables, we talked about proportions, 1 and 2 proportion z-tests. Then we took a break, talked about means. But now we're talking back to categorical variables, talking about proportions again, but we're talking about what happens when there's more than 2 proportions. Right? That's what we're talking about today. There's these special tests, and they're called chi-square tests. And so we're trying to find this new model so we can talk about what happens when there's more than 2 proportions to deal with. So I'll give you this flow chart eventually when we start reviewing. But we have this test called this chi-square goodness of fit test that happens when you have more than 2 proportions. And you're trying to see if the distribution of your variable or your categories is the same as what you would think it would be. All right, so hence goodness of fit. Is it a good fit to this model? Okay. Now, we're going to do a lab today in class with M&Ms, and we'll talk through this. But if we're thinking about a hypothesis test, the first thing we do is talk about hypotheses. All right, so for goodness of fit test, we're making sure the observed distribution matches a theoretical or expected distribution. For example, in the book, they take the top 400 millionaires, like Forbes list, all right, and they break them down by zodiac sign. And they're trying to see if the distribution of those birthdays by that zodiac sign match what we would think that they would be equally likely. All right, so you take the 400 and you divide by 12 and see how many expected are in each category, right? So we're matching that. There's another example. If we are looking at a die, and we want to see if it's a fair die, okay? And you have rolled it 120 times, and you want to see if it's fair, then you would assume that each face is equally likely. So it's a theorized distribution, and you're going to have the observed number each time each face shows up in a table. All right? So you're trying to sit there and take some observed values and match them to what you think should happen. And we'll do that today. So here are your null and alternative. Either it matches, and then alternative does not match. Okay? After you write some hypotheses, you've got assumptions and conditions. These are a little bit different, and chi-square tests are going to just be a little bit different because they're not what we are used to. The first thing is that we need to have counted data, and all that means is that we need to have totals for each category. We can't do the test with proportions, so now you can't have percentages in the tables. We have to have actual data. Now, if you can find the counts, that's fine, but we have to have counts, okay, totals for each category. We also have to assume a little bit of independence. The counts in the cell should be independent. So what that means is that each of the categories need to be disjoint. I can't have a category that says, all right, people with blue eyes, and then another category that says people with brown hair, because people could be in both. They need to be disjoint categories. And again, you should still have a random sample. So that's what we're used to. Now this last one is different. Then you're going to have a count for each category, but we need to make sure that the expected number is at least 5 for each category. So if we don't have at least 5 for each category, it's going to be hard to do this chi-square test. So at least 5, that's different. For proportions, we always do greater than 10. For chi-square, it's a little bit different, so we can do greater than 5. Okay, so there are your conditions. Now, after you talk about your conditions, you can say we're going to do a chi-square model. And so we're going to do a chi-square goodness of fit test. But you have to know how to do the test. So in the past, we had like standard deviation and a z or t statistic and then a p-value. Well, same thing here. There's not standard deviation. But we're going to find our chi-square test statistic. And you're going to do that by following this formula here. So we have the count for observed minus the count of expected squared divided by expected. And we're going to do that for each individual row of our table and then add them all together to get chi-square. So you're going to have a table of observed values. Maybe there's 7 observed here. A column for expected values. Maybe you expect to get 11. And then our last column is going to be observed minus expected squared divided by expected. So I'm going to take 7 minus 11 square and divide by 11. And once we get all of these values for every single row, we add it all together at the bottom, and that's going to be our chi-square. And again, we're going to do this today by doing an M&M lab so that you have something to do, and it's not just me sitting up here and telling you what's happening. Now, chi-square is a family of models, just like student T models. So you have to have degrees of freedom to determine which model you're using. So in this case, our degrees of freedom is still n minus 1, but n is the number of categories. So if you have 7 categories, you have 6 degrees of freedom. So it's not the sample size or anything like that. This is just the number of categories. And we'll get all into that. Once you find your chi-square statistic, you're going to use chi-squared CDF in your calculator. All right? And then you're going to find from that you're going to find a p-value and make your conclusions. So all of that is the same. It's just a new test statistic. Now, a chi-square statistic is only used for testing hypotheses, so we'll never have any confidence intervals. If the observed counts don't match the expected, the statistic will be large, right? Because either it fits or it doesn't, okay? There's no confidence interval that I think it fits with this percentage of the time. That's not happening. It's either it fits or it doesn't. So because of that, we're always looking at this upper tail of our chi-square model. So we're always looking at chi-square CDF. We're going to do chi-square as the lower and infinity as the upper bound, okay? And that gets us our p-value. Our conclusions at the end about the p-value being high or low are going to be about the same. If it's low, you reject. If it's high, you fail to reject. With chi-square, though, you don't have a unimodal and symmetric model. All right? That's very important. So because of that, you can get, and you're always looking at the upper tail, so you can get some crazy high p-values, and that's okay. Before, that was always kind of like caution, like, oh, did I do something wrong? But now it's pretty much okay. So you can see that this curve right here has degrees of freedom of 5. And just so you can see how they're skewed, if I have the degrees of freedom of 5, and I'm looking at a chi-square value of 5, well, that's just this tail for the degrees of freedom of 5. That's going to be a little big, but then if you look at the same tail for degrees of freedom for 9, that's this huge tail, and that's going to be a large p-value, right? So the degrees of freedom just incrementally can be a big deal. So you need to make sure you have degrees of freedom correct, okay? But it's important to note that they are skewed. They're not unimodal and symmetric. Nowhere do we check a normal condition or anything like that. That's not important because they're not symmetric models, okay? So to talk through this, let's go through and do the M&M lab, okay? That way we know what's going on, if it'll let me. Here we go. Now we did this in class, and so I'm recording this later, so I'm going to be using some data from class today. And again, I did not write this, okay? The FDC, Federal Department of Candy, is investigating Mars Company. There have been allegations that Mars has been fraudulent in their advertising. The accusations relate to Mars's claims about the color distribution of their flagship product, milk chocolate M&Ms. Some consumers have complained about not getting the promised distribution of colors. Now the FDC and Mars are mired in a bitter lawsuit that threatens the entire U.S. candy industry. As usual, we've been hired to investigate and present our results at the trial, whose outcome hinges entirely on our work. Let us do well. Nearby is M&M's claimed color distribution taken directly from their website. So here's the proposed color distribution by Mars. Okay? Now, first question is, what kind of statistical test is called for and why? Well, we want to see if our sample distribution of colors matches the proposed distribution of colors. So that's the chi-square goodness of fit test. There are 2 other chi-square tests in this chapter that we will get to, so you're going to have to keep them straight. And it says include hypotheses. So our null hypothesis is that the color distribution of our sample will match the color distribution claimed by Mars Company. And our alternative is going to be that the color distribution of our sample does not match the color distribution claimed by Mars Company. Okay? That's all I gotta know. Number 2, how do you plan to draw an appropriate sample of M&Ms? We want it to be as random as possible, and so we'd love to just go by bulk M&Ms and just see what the distribution of colors was. And a simple random sample would involve numbering a bunch of M&Ms and selecting them, and that's just not going to work. So what I'm going to give you today, or what I gave them, is a bag of the shareable size of M&Ms. That way they have about 100 M&Ms in them, and that way we can make sure we can do this test. Do you think using a bag of shareable M&Ms is going to do our analysis? Do you think it's random? Well, according to Mars Company, the distribution of color should be the same no matter what, right? So I would assume this is a random sample. But we will see. Okay, so what's going to happen? Or what happened in class today? They took the shareable size of M&Ms, and they opened it, and they split them into colors. And they counted how many of each color they saw. So here is some sample data. We have all of the colors and the observed number of each in the bag, and then the total number that they have. Okay? So the next part of this, because we're trying to come up with our chi-square test statistic, is to come up with the expected count. The expected count is going to be our total M&M number. So in this case, 101, times the percentage for that color. All right, so those are back on this page, 13, 14, 13, 24, 20, 16. Okay, so on the calculator, and I'm going to use mine over here because it's faster. To find the expected number of brown, I would do 101 times 0.13, which is 13.33. Sorry. And I would do the same thing for yellow. I would do the 14% times 101. Red should be 13%. So that should be the same as the first one, 101 times 13%. For blue, you should have 24% times 101. For orange, 20% times 101. And for green, 16% times 101. Okay? And you don't have to round to the nearest M&M because this is what our expected count is. We're going to be exact. Now you can round a little bit if you need to, but if there's not a whole lot of rounding, this should all up to be 101 as well. Okay? So now we're going to go through and we are going to find our test statistic. So for this first box, technically I'm taking 5 minus 13.13, squaring it, and dividing by 13.13. All right? That seems like a lot of work for 6 categories. So I'm going to show you how to do this in your calculator so that you can save some time. Okay? All right, so I've cheated a little bit. And I have all of my data into the list already. All right, so I have my observed counts in list 1 and my expected counts in list 2. All right, now I'm trying to find observed minus expected squared divided by expected. So I'm going to use it to my advantage. So you can go up to the top and go to the title. You can probably do this all in one step, but it makes me nervous, so I split it up. So in list 3, I'm going to do list 1 minus list 2, observed minus expected, squared. And then in list 4, I'm going to do expected in list 3 divided by the expected. And there you go. There are all the statistics that I should have had listed out in green. So this would have been 5.034, and the next one would have been 0.24467. Okay. So they're all there. Okay? Now, the chi-square statistic is all of those added together. That is what chi-squared is. So I don't want to have to go through and type all these in and try to make, and I might make a mistake in the calculator. That seems like a disaster. So what you do, go to second quit, and then go to second stat. So not the stat menu, but the list menu of it. Scroll over to math, and then scroll down to where it says sum, and then type in the list that you want to add. Well, I want to add all this stuff in list 4, and you get 10.885. That is my chi-square test statistic. It's all of those observed minus expected squared divided by expected numbers added together. That's chi-squared. In order to find the p-value, you need to find the degrees of freedom. That's the one. We're going to be 5. And then for the p-value, you've got to use your calculator again. So go to the distribution menu and go down to chi-square CDF. Your lower will be 10.885. We always do the upper tail. Upper will be infinity. That's how it's always going to be. Degrees of freedom are 5. So I get a p-value of 0.0537. Ooh, that's close. Okay. So the next question here before I get to a conclusion talks about my assumptions and conditions. It's important to note all of these. So I have counted data. I have totals for each category. That's what I've got. I've got totals. I don't have percentages or some quantitative funkiness. I have totals. Each of my categories are disjoint, right? So there's no reason to believe that an M&M can be yellow or brown at the same time. We assume that a sample bag of M&Ms, a shareable bag, is a good representation of M&Ms. And then you can see in this chart that all of the expected cell frequencies are greater than 5. Right? So that's our last condition. Now we need to make a conclusion. Well, my p-value is 0.0537. So my p-value is high. So I'm going to fail to reject the null hypothesis. Now, it was a lab, so some people did reject. It kind of depended on your bag. And if I fail to reject, that means I think the null hypothesis is true. So it seems the color distribution in the sample matches the distribution from Mars. Matches the distribution set by the Mars company. Okay? So the conclusions are the same. High, low, reject, failed to reject, all that jazz. Put it in context. Go back to your hypothesis. All right, so this is what you're going to be doing today in the homework. You're doing goodness of fit tests. You're just looking to see if your distribution that's observed matches a distribution that's theorized. Is it equally likely, or all the expected counts going to be the same? Does it match a certain distribution like these M&Ms where all the expected counts are a little bit different? Just kind of depends. All right, so we'll do these chi-square tests for goodness of fit, and then later we're going to talk about the other 2 chi-square tests.